Well, good morning friends, good morning students. So, yesterday you have started with the ionic equilibrium. So, there you have learned regarding the strong electrolyte, weak electrolyte, then the factors affecting the degree of dissociation, etc. All this you have learned in the yesterday's class. Now, today's class, let us move into acids and bases. Now, before this, let me just take you to your 9th or 10th standard classes little, wherein you have learned regarding acids and bases. The science teacher has told you that what are acids is acids are sour in taste. Acids are sour in taste and bases are bitter in taste. So that you have learned. Later, means sour is nothing but whatever the huli that you say in the Kannada, and bitter will be bitter gourd if you have tasted any time. So that will be the bitter taste. Further, now in that acids and base only, your teacher has also told you regarding the litmus test. Okay, two types of litmus you have discussed, red litmus paper, blue litmus paper. If the red litmus paper is dipped in a solution, if a red litmus paper is dipped in a solution of a base, if the red litmus paper is dipped in a solution of a base, it shall turn to blue. That shows the presence of the base. Okay, and if the blue litmus paper is dipped in a solution which is acidic in nature, that will turn red to orange some color, or even sometimes little pink. So there, that will show, that will indicate that it is going to be an acid. So first test was the taste, that is maybe the sour taste or the bitter taste. Then you came across the litmus paper test, the litmus test. Blue litmus turning to red shows it is acidic. Red litmus turning to blue, it shows it is basic. Then further, you have come across, maybe if at all there was a laboratory in your school, and if they have shown you, there's something called pH paper also. Okay, a red to orange color or even pink to orange color paper is there. So that pH paper, when it is dipped in a solution and there is a color change, suppose whatever the pink to orange I am saying, if it turns to more pink, if it turns towards more pink to red, that shows the given solution is acidic in nature. Once again, the whatever the orange to pink color paper will be there, which we call it as a pH paper, on that pH strip paper they have indicated the colors which it will be showing for the different whatever the acids and bases is there. So that if you dip it in a solution and if it turns towards to more pink, let's say, that will be more acidic, that is acidic in nature. And if it turns towards blue, okay, if it turns towards blue green like that, that shows it is basic. So those were the earlier ideas of learning what we call it as the acids and bases. Now in this today's discussion, we come across three different definitions. Acids and bases. So 3 to 4 scientists, okay, they have their own ideology regarding the acids and bases. In that, first let us take regarding Arrhenius acid base theory. Okay, Arrhenius acid base theory. First one, it is Arrhenius acid base theory. First, I shall discuss all the three definitions, quick definitions. Then we shall go into the details of those. What are those Arrhenius acid and what are its drawbacks, what are its detailed examples and other things. Let us see. Now, Arrhenius acids and bases. In this, you have acid is what? What is an acid? Acid is that substance which when put in the aqueous media, which when present in the aqueous media, it shall generate H plus ion. Acid is one which when dissolved in the aqueous media generates H plus ion. Okay, so H plus ion generator it is. H plus ion generator, and that we call it as what? Arrhenius acid it is. H plus ion generator is Arrhenius acid. Further, if you take base, what is a Arrhenius base? Now Arrhenius base, so these substances when poured in water, when present in the aqueous media, these substances, Arrhenius bases, what they say, which when present in the aqueous media, they generate OH minus ions. So if it is generating OH minus ions, if it is generating OH minus ions in the aqueous media, when it is present in the aqueous media, and for that we call it as the Arrhenius base. Once again, what is Arrhenius acid and Arrhenius base? Arrhenius acid is the one which generates H plus ion in presence of the aqueous media. And if you take Arrhenius base, according to Arrhenius theory, okay, so that which generates OH minus ions, it shall be the Arrhenius base. Okay, then coming to, I told you I shall just define first all the definitions. What are the shortest definition for all the 3-4 basic theories of the acids and bases? Then we shall come into the details of this. Second one, you have Bronsted-Lowry acids and bases. Bronsted-Lowry acids and bases. Almost a little similar definition only, but with a little different ideology. Now what is the Bronsted acid base? Bronsted acid, let's take. According to Bronsted definition, Bronsted-Lowry definition, the substance which generates or which donates proton, a proton donor is taken to be a Bronsted-Lowry acid and base. Proton donor. A proton donor. Proton donor, in other sense, how can you write in the symbolic form? It is H plus. A proton donor is one which is donating H plus ion there. Okay, a Bronsted-Lowry acid and base says the one which is giving proton donor, what we call, that is nothing but Bronsted-Lowry acids and bases. Similarly, Bronsted base, if you take Bronsted base, it is a proton acceptor. Proton acceptor, which accepts a proton, like for example H2O you take. H2O shall take up a proton and form H3O plus, means that time H2O is a base. NH3 is there. NH3 also takes up a proton, it forms NH4 plus, that will be also a base. NH3 we call it as the Bronsted base. Okay, proton acceptor is Bronsted base, and proton donor shall be Bronsted acid. Proton donor is Bronsted acid, proton acceptor is Bronsted base. Okay, then coming to third method, that is Lewis acid base theory. Lewis acid base theory. Now what is Lewis acid? Okay, Lewis acid is electron pair acceptor. Lewis acid is electron pair acceptor. Electron pair acceptor. Not only one electron, in pairs it is accepting. The substance which accepts electrons in pairs, we call that as the Lewis acid. And the substance which donates electrons in pairs, the substance which donates electrons in pairs, basis if you take, now electron pair donor it is, electron pair donor. Electron pair donor is going to be Lewis base. So here what I have done, in the few minutes time, I have given you the three definitions. See, all the three definitions are true with respect to their examples. There are definitely drawbacks or limitations, but all those scientists, remember, they were contemporary time scientists, means at the same time different people have studied regarding that. They have their own explanation, they have their own support for whatever the theory they have put. So we shall also see here what are the examples which come under each one of them, and later we shall also see what are the limitations of that, which we don't call it as Arrhenius acid but is a Lewis acid, which we don't call it as a Bronsted acid but there is going to be a Lewis acid. Like this, there are some few examples that we shall see broadly, quickly. Okay, let us come to all the three definitions. Arrhenius acid is what? Arrhenius acid is the H plus ion generator. H plus ion generator is Arrhenius acid. Arrhenius base is the OH ion generator. OH minus ion generator is Arrhenius base. Then coming to Bronsted-Lowry definition of acids and base. There what we have, so there the proton donor is the acid, proton acceptor is the base. Proton donor is the acid, proton acceptor is the base. Then the third set of definition, Lewis acid base theory. In this what is there? So whichever is electron pair acceptor, whichever substances is a electron pair acceptor, that we call it as an acid, and electron pair donor, that's a base. Okay, so these are the three different methods of approach for understanding what is an acid, what is a base. Now let us go to the Arrhenius definition again. In that we shall see the different examples. Okay. Now here in the acids again we have different types of acid. Mono-basic acid, dibasic acid, tribasic acid. Okay, mono-basic acid, dibasic acid and tribasic acid. Like this we have different kinds of acids there. So let us take regarding acids first. In this, now when you take example, for example it is HCl. In the aqueous media, this will generate H plus and Cl minus. H plus and Cl minus. Let me write it properly. H plus and Cl minus, if it is generating, that we call it in the aqueous media, in the aqueous medium, and that we call it as the Arrhenius acid. Now here it is giving only one H plus ion. So this is called as what? Mono-basic acid, which is generating only one H plus ion. For that we will call it as the mono-basic acid. Similarly, one more you take, nitric acid in the aqueous media. This also it gives you H plus and NO3 minus. So what is our observation? Again it is giving one H plus ion. One H plus ion it is giving there. Then coming to third example, CS3COOH. This also in the aqueous media, this gives you CS3COO minus and H plus. Okay, so here also what we observe, it is giving one H plus ion. So these all three examples what I have taken, HCl, HNO3, CS3COOH, where it is generating one H plus ion, and since first thing is it is generating H plus ion, that's why it is called as the Arrhenius acid. Then later we have another word for that, monobasic acid. Monobasic because it is generating one H plus ion there. One H plus ion is generated in the aqueous media, that's why it is called as the monobasic acid. Okay, short agi helbekandre one H plus ion generate ಮಾಡ್ಲಿಕ್ಕೆ ಅಲ್ಲಿ aqueous media ದಾಗ ಅದಕ್ಕೆ ಏನಂತೀವಿ, that is called as the monobasic acid. Compulsorily it should be in the aqueous media. Okay, by itself it may not generate the H plus ion. Then coming to, so these all what I wrote just now, these all are 2-3 are monobasic acid. Monobasic acid. Let us come to the next set. In that next set, dibasic acid. You take for example H2SO4. H2SO4 in the aqueous media. H2SO4 in the aqueous media, this gives 2H plus and SO4, SO4 2 minus. 2H plus and SO4 2 minus. Now here it is generating 2H plus ions. So this is dibasic acid. This is dibasic acid. Similarly, you take the next one, H2CO3. H2CO3, carbonic acid. This also you can see, you can observe. So this is giving you 2H plus and then CO3 2 minus. 2H plus and CO3 2 minus. So this carbonic acid H2CO3, which is carbonic acid, it is generating 2H plus and CO3 minus. So this is also what? This is also dibasic acid. Dibasic acid. Further, coming to one more example, oxalic acid. Oxalic acid formula, COOH. COOH in the aqueous media. In the aqueous media, this will give you COO minus and COO minus, oxalate ion, and it is giving you also 2H plus ions. 2H plus ions it is giving. So this also is a dibasic acid. So wherever it is giving 2H plus ion in the aqueous media, it is called as the dibasic acid. First of all, it is Arrhenius acid. Okay, Arrhenius acid means what? Where it is giving H plus ion in presence of aqueous media. Where it is giving H plus ion in the aqueous media, that we call it as the Arrhenius acid. Okay, so monobasic and dibasic, two we have done. Let us go for the tribasic. In the tribasic, the example is for phosphoric acid. H3PO4. So this in aqueous media, what will happen here? 3H plus and PO4 3 minus. So what is our observation? Here it is generating 3 H plus ions. First of all, it is generating H plus ion, that's an acid. Over that, again it is generating 3 ions of that, and that's why it is called as tribasic acid. Tribasic acid. Okay. So wherever it is generating 1 H plus ion, monobasic acid. Wherever it generates 2 H plus ion, it is dibasic acid. Wherever it generates 3 H plus ion, it is tribasic acid. Okay. So this is regarding the Arrhenius acid base theory. In this we have seen the acids. Now further there is one limitation. What is the limitation you see? Now H3BO3 is there. H3BO3, this is boric acid. While playing carom etc. you must have used, okay, and even in storing of the grains they mix and keep it so that any insects and other things do not attack that. So that is what is boric acid. Directly when we see there are 3 hydrogens here. So based on this 3 hydrogens, what one may infer, what one may conclude is it is a tribasic acid. But no, according to the definition of Arrhenius, this H3BO3 is not a Arrhenius acid. It is not a Arrhenius acid. Why it is not an Arrhenius acid means, so when you take this H3BO3, okay, in the aqueous media, so it is generating what? It is generating there, or it is rather accepting the OH ions. So how do you write that? BOH 4 times. And over that the charge is going to be -1, and it is H plus ion here. So whatever OH ion is present in this H2O, it gets added to that, and the H3BO3 is not generating H plus. This H plus is coming from water. This H plus, whatever we are seeing, it is coming from water. So this is OH ion acceptor. So according to the Arrhenius definition, this H3BO3 is not an acid. It is not a Arrhenius acid. H3BO3 when present in water, when present in aqueous media, so there what happens is BOH minus, BOH 4 times minus it is, and that will be H plus ion. Okay. So here H3BO3 is accepting the OH ions. It is accepting the OH ions, so that is not taken to be an Arrhenius acid. Then coming to next one, Arrhenius base. Arrhenius base. So Arrhenius base, what we have discussed is which is generating OH ions. OH minus ion generator, for that we call it as the Arrhenius base. Say again here also we have got the example of monoacidic base, diacidic base, and also triacidic bases. So first of all, monoacidic base. Monoacidic base. Say for example, if you take NaOH in the aqueous media, okay, so this will give Na plus and OH minus. In yesterday's class, the strong electrolyte, weak electrolyte you have come across. So here what it is generating? It is generating OH minus ions. So this OH minus ion generator, for that we call it as the monoacidic base, because it is generating 1 ion of OH minus. Similarly, cesium hydroxide. This also in the aqueous media. This will give cesium plus and OH minus, cesium plus and OH minus. Even rubidium hydroxide, RbOH. So in the aqueous media, so this is giving Rb plus OH minus. So here also what it is nothing but because it is generating OH minus ion, one number of OH minus ion, this is called as the monoacidic base. It is called as monoacidic base. Okay. First thing, it is generating OH ions, OH minus ions rather. So that's why we call it as what? Arrhenius base. Then again there is a classification, that is monoacidic base. One more example, NH4OH. NH4OH. So this will be, here I missed it, I am sorry, Rb plus, and this will be NH4 plus and then OH minus. NH4 plus and OH minus. So what is our observation? Everywhere we have OH minus ions, and that OH minus ions generator, for that we call it as what? It is a Arrhenius base. So all these three examples, since one number of OH ion was generated, so it is called as monoacidic base. It is called as monoacidic base. Let us go for the diacidic. Okay, diacidic bases, second set. Diacidic base, let's see. So one example, diacidic base, CaOH twice, calcium hydroxide. Calcium hydroxide in the aqueous media, calcium hydroxide in the aqueous media, this gives Ca2 plus and 2OH minus. 2OH minus. Here there is a difference now. Earlier there was only one OH, now there is 2 ions of OH minus is present. 2 ions of OH minus is present, and for that we call it as what? It's a diacidic base. Diacidic base. Similarly, magnesium hydroxide. Magnesium hydroxide, this also in the aqueous media, so Mg2 plus and 2OH minus. Mg2 plus and 2OH minus, magnesium hydroxide. So this also is generating 2 OH ions, and that's why it is called as what? Diacidic base it is. It is diacidic base. Barium hydroxide also you take. Barium hydroxide. Barium hydroxide in the aqueous media, this gives Ba2 plus and 2OH minus. Hope so you have understood what is that diacidic base. Diacidic base, because it is generating OH ions, and that's why it is called as Arrhenius base. OH minus ions are generated, that's why it is called as the Arrhenius base. Further, now here everywhere there are 2 ions of OH minus, and that's why it is called as diacidic base. Diacidic base. Then coming to now the next one, triacidic base. Triacidic base. Triacidic base. Okay. So here, as per our earlier discussion, triacidic base will be what? Which should generate, wherever it is generating 3 OH minus ions, that will be triacidic base. Example, FeOH thrice. FeOH thrice. So in the aqueous media, this gives you Fe3 plus and 3OH minus. Fe3 plus and 3OH minus. First of all, OH minus is generated. That's why Arrhenius base. Further 3 OH ions are generated. That's why triacidic base. Triacidic base. Okay, one more. Aluminium hydroxide, AlOH thrice. AlOH thrice in the aqueous media. So this will be Al3 plus and the other is 3OH minus. Okay, 3OH minus. Since it is generating OH minus ions, first of all it is Arrhenius base, and since 3 numbers of the ions are generated, and that will be triacidic base. Triacidic base. Okay, so here we have come across the examples of Arrhenius acid, Arrhenius base. One example I showed you, that was the H3BO3. It is not taken to be Arrhenius acid because it is rather OH ion acceptor. OH ion acceptor we will learn in the Bronsted-Lowry definition. That will be something different, proton donor, proton acceptor, and that will have a different idea. That let's see now. One more drawback here of this Arrhenius definition. Okay, drawbacks or limitations if you take. If you take for example BCl3 or AlCl3. Okay, so now these do not contain the H plus or these do not contain OH minus. So they shall not be generating the H plus ion or OH minus ion. These cannot be classified as acid or base depending upon or based upon the Arrhenius, whatever the definition is there, Arrhenius concept is there. But these are Lewis acids and bases. So here comes the drawback, here comes the limitation of that Arrhenius theory. Few of the examples in the Lewis acid base cannot be the examples in the Arrhenius acid base theory. So whatever the examples of Lewis acid base theory is there, some of them they could not be explained as Arrhenius acid or base. So the approach is different. Okay, approach is different. All the 3 definitions are correct, but there are limitations in that. There are some limitations. So one such drawback in the Arrhenius definition is these examples BCl3, AlCl3, BeCl2 and even some of the other examples we cannot be classifying them as the Arrhenius acid base theory. Let's see. Next one, Bronsted acid base theory. Bronsted acid. Okay, what are Bronsted acids? Proton donor acid. Whichever is donating proton, and that we call it as the Bronsted acids. Many examples are there. HCl in water. Okay, this will in the aqueous media or aqueous media already we have written. So this will give you H3O plus and Cl minus. So here what is our observation? Now this HCl is giving its proton to water and it will form hydronium ion. So here this HCl is Bronsted acid. This is acid here. This is acid, water is the base here. Okay, water is accepting the proton, so that's why it is base. Whichever is donating proton is acid, whichever is accepting proton it is a base. Other example, let us take again HNO3. HNO3 also in presence of water, this gives you H3O plus H3O plus and NO3 minus. NO3 minus. So here also what is the thing? The HNO3 is giving its one proton to water. It is forming here H3O plus. So since this is a proton donor, since nitric acid is a proton donor, HNO3, nitric acid, acid itself we are calling there. So HNO3 becomes the acid. So what is Bronsted acid is the one which is donating, which is a proton donor. For that we call it as the Bronsted acid. Then coming to Bronsted base. Bronsted base. Okay, Bronsted base is one which is a acceptor of proton. Just now whatever example we wrote, in that when one is acid there, the other one is the base, because one is proton donor, other will be proton acceptor. If you take now example NH3. NH3 plus H2O. NH3 plus H2O if you take, so this will form NH4 plus NH4 plus and OH minus. Okay. So now in this case what has happened? Water has donated one proton to the NH3. So water becomes the acid, and NH3 is the base. So whichever is accepting the proton, whichever is the acceptor of proton, so this NH3 has accepted the proton, that's why that NH3 is the base. NH3 is the base. Later again you can take one more example, HSO4 minus. HSO4 minus in presence of NH3. NH3. So this will give you NH4 plus. NH4 plus and SO4. SO4 2 minus. SO4 2 minus. So what is here? Ammonia is accepting a proton from HSO4 minus. Ammonia is accepting a proton from HSO4 minus. So ammonia is a base. Ammonia is a base, and this one, since it is donating a proton to NH3, this becomes an acid. So this is acid, this is acid, this is base. This is acid, that is base. Okay. So this is accepting the proton from HSO4 minus, that's why it is base. So what we have come across in this Arrhenius acid base definition is that which donates proton, is Arrhenius acid, Bronsted acid, and that which accepts proton, that which accepts proton is Bronsted base. Bronsted acid, Bronsted base, proton donor, acid, proton acceptor, base. After doing this, further Bronsted and Lowry, they came across another concept called conjugate acid base pair. Conjugate acid base pair. So when two molecules are reacting, here itself we have come across now this NH3 and H2O, and this side NH4 plus and OH minus. So in this example what we see, okay, it's a reversible here, it's a reversible thing. So what will happen is Now NH3 reacts with water to give NH4 plus and OH minus. Okay, and in the reverse way, if you see, NH4 plus is losing proton to come to NH3. NH4 plus loses proton, and that proton is taken up by OH minus to form water. That proton will be taken up by OH minus to form water. So in that case, what happens? This becomes an acid. The proton donor NH4 plus, that becomes an acid, and the other one OH minus, that becomes a base. That becomes a base there. NH3 reacts with water to give NH4 plus and OH minus. Okay. So now this NH3, since it has accepted a proton from the H2O, that will be base. And since this has donated the, water has donated the proton, that will be what? It's a Bronsted acid. Bronsted acid, Bronsted base. But at the same time, if you come from that side to this side, okay, from the reverse direction if you are coming, NH4 plus and OH minus. Here NH4 plus is donating a proton to the OH minus. That time this NH4 plus becomes a base. NH4 plus becomes an acid, and the OH minus becomes a base there. Okay. Now this set of whatever these molecules are there, we come across another word called conjugate acid base pair. Now this, if you take NH3, if you take, and if you compare, if you join this, or if you just compare it with the NH4 plus, these two are conjugate to one another, we say. These two are conjugate to one another. Now NH3 is there, which is base, and NH4 plus is an acid. So this, whatever the set of molecules are there, this we call conjugate to one another. Conjugate acid of NH3 is NH4 plus. Conjugate acid of whatever NH3 is there, it is NH4 plus. So this is base, that is acid. A conjugate acid base pair, it differs by a proton. It differs by one proton. If you add a proton to the existing base, if you add a proton to the existing base, that forms what? It forms the acid. And if you remove one proton from the given acid, that forms the conjugate base. ಅಂದ್ರೆ ಇಲ್ಲಿ ಬೇಸ್ ಮತ್ತು ಆಸಿಡ್ಗೆ one proton difference ಇರ್ತದೆ. Okay, one proton is the difference between acid and base. Acid ದಾಗ one proton ಹೆಚ್ಚಿಗೆ ಇರ್ತದೆ. In acid, the one proton number is more than the base. So this set becomes a conjugate acid base pair. Similarly, even H2O and also OH minus, this set also you take. This set also, what happens is, this set also, water and OH minus also are conjugate acid base pair. Now this water molecule is conjugate acid of the OH minus ion base, or else you can call OH minus ion is a conjugate base of H2O. OH minus ion is a conjugate base of the H2O. Okay, so conjugate acid base pair, they differ by a proton. In acid, one proton number is more. In acid, one proton number is more than the base. In acid, one proton number is more. Conjugate acid base pair. Okay, further, in generalized terms, if you take, in general, HX you take, HX reacts with the B. So this will form HB, let's say, HB and X minus, HB plus and X minus it is. Now this set here, now this is acid, HX is acid, and its whatever the conjugate is there, it is going to be the conjugate base and that will be X minus. This is conjugate base. Conjugate base it is. Okay, X minus is conjugate base of HX. Okay, they both are differing by one proton. They both are differing by one proton. Similarly, B, if you take B general, this is base, let's say, this is base, and this will be conjugate acid. Conjugate acid. So this set, base and the conjugate acid, they form another set here. So in this also, if you observe, there is a difference of one proton. In this set, that is B and HB plus, there is a difference of one proton. So this set we call it as what? This set is also called as the conjugate acid base pair. So in the Bronsted-Lowry theory, what we have is, apart from the definition of just the acid and base, acid means proton donor, base means proton acceptor. Apart from this, a further one more step is there, which we have conjugate acid base theory. In this conjugate acid base theory, the acid has got one proton number more than its conjugate base. Whatever the set is there, okay. So there is a difference of one proton. In the competitive exams, there has been many a times a question regarding this conjugate sets, which is the conjugate for which one. Regarding that, there has been questions. A list I shall just put it here, which will be helping you. HCl if you take Cl minus. Now this is conjugate base. This is conjugate base. This is acid. They both differ by what? They both differ by one proton. Similarly, H2SO4. H2SO4. So here it will be HSO4 minus. HSO4 minus. Then you take HSO4 minus only now. HSO4 minus. So here it is SO4 2 minus. SO4 2 minus. These both are the pairs, conjugate acid base pair. They may ask you to match also. They may ask you to just find out which is the conjugate base of that particular acid. Matching type of questions also can be there, or even just the finding of the opposite, whatever the conjugate part is there of the base also they can ask, of the acid also they can ask. Okay. Then one more, nitric acid. So this will be NO3 minus. Then you take H2CO3. H2CO3, and this will be HCO3 minus. Also HCO3 minus you take, and this will be CO3 2 minus. From this what we come across again, H2CO3 is acid of conjugate base HCO3 minus. But again this is going to behave as acid further. Okay, this also can behave as acid in presence of, or when you compare it with the CO3 2 minus. So between them there is again a difference of one proton. There is a difference of one proton. One more set example, H2S. So here it will be HS minus. These two are the sets of conjugate acid base pair again, H2S and HS minus. H2S and HS minus. Further, this HS minus becomes an acid in presence of what, or compared to what? S2 minus. Okay, this is conjugate acid base pair here. it's a conjugate acid base pair. Then you take NH4 plus, so this will be NH3. Okay, one proton number is more here. One proton number is more. Or we will take a simple example. If you take H2O, and here it is OH minus. Okay. So these are the examples of conjugate acid base pair sets. You take here H3O plus and H2O. This also is a set of conjugate acid base pair, whatever the thing is there. Okay. So Bronsted definition, which is proton donor and proton acceptor. Further, it is also given the idea regarding conjugate acid base pair idea, the theory. Okay. So where the conjugate base is one proton less. All this set what I wrote here, it is a conjugate base and it is one proton less than the whatever acid is there. And based on this only further, the next thing that we will be learning is, so there is something called amphiprotic or amphoteric. So there are some substances which are behaving as acid also, base also. Same substances behaving as acid in one context and same substances behaving as base in some other context. So hope so this idea regarding conjugate acid base is clear. One example regarding the amphoteric nature let me give you, and then we can wind up for today. Amphoteric. Amphoteric substances. Okay. Now you take for example HCl and water. HCl and water. Now this is acid, this is base. This will form what? H3O plus and Cl minus. Okay, H3O plus and Cl minus. Now here water we have shown it as where it is accepting a proton from the HCl and it is forming H3O plus. So water is acting as a base. Same water molecule in the presence of ammonia, if you take NH3. So this reacting with H2O. Now here what happens is, it will form NH4 plus and OH minus. NH4 plus and OH minus. So here what is our observation? Now this H2O, it is donating a proton to the NH3. Now this time this becomes a acid. This becomes a acid, this is a base. H2O is an acid and NH3 is a base. So same molecule you can observe, water in one context where HCl was present, this was acting as base. And water in this another context, that is NH3 when it is present, this is acting as a acid. So same water molecule behaving as acid as well as base. For this we call it as what? For this we call it as amphoteric substance or amphiprotic substance. Amphoteric substance or amphiprotic. Amphoteric substance or amphiprotic substance. Substances which act as acid also, base also in two different situations, not in one situation only, two different situations, one in one context, another is in another context, and such a thing we call it as what? Amphoteric, amphiprotic. So these were all the things that we have got from the Bronsted-Lowry definition of acids and bases. So what we have learned today is regarding all the three definitions quickly we have seen. Then what we have done is Arrhenius acid, Arrhenius base, different acids and bases example we have seen. Then we have come across Bronsted acid base theory. Further in that we have also seen the different examples in the Bronsted-Lowry acids and bases, proton donor, proton acceptor. Then we came across conjugate acid base pair. Further, we have come across what is called as the amphoteric or amphiprotic substance. Okay, with this we wind up for today. We shall see in the next class. Thank you.